Alright, in this video I'll be solving the CIE A-Level Maths Probability and Statistics 1 Paper 53 for October-November 2024. If you're feeling anxious, overwhelmed, or unsure where to start, then I've created a complete course that streamlines everything with step-by-step videos, interactive quizzes, and an exclusive student community to keep you on track. You can get access to it by clicking the first link in the description. Otherwise, like the video, subscribe, and let's dive right in. Question number 1. 30% of the residents of Winfield own an electric car. 3 residents are chosen at random. Find the probability that either all 3 own an electric car or none of them owns an electric car. So the probability of one person owning an electric car would be 0.3, right? 30%. But now we've got 3 of them. So the probability of 3 people owning an electric car is 0.3 cubed. Or none of them owns an electric car. So the probability of one person not owning an electric car is 0.7. And then if it's 3 of them that do not own an electric car, then that's going to be cubed. And we are adding because they have said or. If they had said and, we would have multiplied our 2 probabilities. So let's punch this into the calculator. That's 0.3 cubed plus 0.7 cubed. And this gives us 0.37. 0.37, and that's our final answer. A random sample of 125 of the residents of Winfield is selected. Part B. Use a suitable approximation to find the probability that more than 45 of these residents own an electric car. Okay, so let's define our random variable W. Let W be the random variable. Number of Winfield residents who own an electric car. Number of Winfield residents who own an electric car. Own an electric car. So W follows a binomial distribution, and we've got 125 of them, and the probability of success, the probability of owning an electric car is 30%, 0.3. Okay, and we have been told to use a suitable approximation. So at AS level, the only approximation that you know and use is the normal approximation to the binomial distribution. But it's always safe to check to see if the conditions are satisfied. So the conditions are that NP should be greater than 5 and NQ should be greater than 5 as well. So let's evaluate our NP. NP is going to be 125 times 0.3. 125 times 0.3. So NP is equal to, let's punch that into the calculator, 125 times 0.3. That gives us 37.5. So here we're saying NP is 37.5, which is greater than 5. Now let's check NQ. So NQ is 125 times, remember Q is 1 minus P. So Q is going to be 1 minus 0.3. So Q is 0.7. So 125 times 0.7, and Q is equal to, this is 125 times 0.7, and that gives us 87.5. So NQ is equal to 87.5, which is greater than 5. So we can use a normal approximation to the binomial distribution. And so what we get is that our W will follow a normal distribution with our mean being NP and our variance being NPQ. NP we've already evaluated to be 37.5, and we need to evaluate our NPQ. So NPQ is equal to 125 times 0.3 times 0.7. So NPQ is equal to, let's punch that into the calculator. That's 125 times 0.3 times 0.7, and that gives us 26.25. Okay, so that's 26.25. And we are required to find the probability that more Okay, so probability that W is greater than 45. But remember that this question was defined under discrete conditions, under a binomial distribution which is discrete, and we have approximated to a normal distribution which is continuous. So we have to apply continuity correction. When we're talking about the number 45 under a continuous distribution or as a continuous number, this represents any number from 44.5 all the way up to 45.5. So if we want greater than 45, it means we don't want any values that are represented by this range. So we're going to start from here and we're going to move to the right. So we want greater than 45.5. So this is going to be the probability. We've run out of space. This is going to be the probability that W is greater than 45.5. And we can standardize. So Z is greater than 45.5 minus our mean, which is 37.5. And this is over our standard deviation. So the square root of 26.25. And so this is the probability that Z is greater than, let's punch this into the calculator, 45.5 minus 37.5 over the square root of 26.25. And this gives us 1.561. So this is 1 minus phi of 1.561. And if you read off the value of phi of 1.561 from your normal distribution tables, you get 0.9407. So it means that our final answer here will be 1 minus 0.9407, and this is 0.0593. And then question number 2. A red fair six-sided dice has faces labeled 111, 222. A blue fair six-sided dice has faces labeled 112233. Both dice are thrown. The random variable x is the product of the scores on the two dice. Part A. Draw up the probability distribution table for x. Okay. So to help us with drawing up our probability distribution table, we should draw a possibility space diagram so that we can see all the possible outcomes we can have, right? So we've got the red die, here, and then at the bottom I'll put the blue die. Let me maybe move this up slightly, blue die. And we know that our red die has faces labeled 111222. So we're gonna have 1, 1, 1, 1, and then we could do 2, 2, 2. All right. And then for the blue die, it's 1, 1, 1, 1, and then 2, 2, 2, 2, 3, 3. And we are told that X is the product of the scores on the two dice. So let's multiply. So 1 times 1 is going to be 1, and then 1 times 1 is 1. 1 times 1 here is 1. 1 times 2 is 2. 1 times 2 is 2, and that's 2 as well. So here we've got 1 times 1, 1 times 1, 1 times 1, 1 times 2, 1 times 2, 1 times 2. Then here is 2 times 1. So 2, 2 times 1 again. 2 times 1, that's 2. And then 2 times 2, so that's 4, 4, 4. Here it is 2 times 1, so that's 2. 2 times 1, that's 2 again. Then 2 times 1, that's 2. Then we've got 2 times 2, that's 4. 2 times 2, that's 4. Finally, again, 2 times 2, 4. Then that's 3 times 1, 3. 3 times 1, 3. 3 times 1, 3. 3 times 2, that's 6, 6, 6. And then this final column is just the same as the previous one. So 3, 3, 6, 6, 6. All right. So from our possibility space diagram, we should be able to deduce the values that our random variable can take and their respective probabilities. Okay. So the values that a random variable can take are 1, 2, 3, 4, and 6. So 1, 2, 3, 4, and 6. So the total possible outcomes, this is a 6 by 6 grid, so the total possible outcomes will be 36. So the 1 appears how many times out of 36? It's 1, let me use a red pen. 1, 2, 3, 4, 5, 6. So it appears 6 times out of 36. And then the 2 appears 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So 12 times out of 36. 12 out of 36. And then the 3 appears how many times? 1, 2, 3, 4, 5, 6. So it appears 6 times out of 36. The 4 appears how many times? 1, 2, 3, 4, 5, 6. 6 times out of 36. And then finally the 6, how many times does it appear? Does it appear? 1, 2, 3, 4, 5, 6. So it appears 6 times out of 36. That's 6 out of 36. Let's close the cells of our table. Okay. So this here is our probability distribution table for x. And then part B says find the expectation of x. So the formula for expectation of x is the summation of xp. All right. So our expectation of x is going to be, you're going to say x times its probability plus x times its probability plus x times its probability until you get to the very end. So it's going to be 1 times 6 over 36 plus 2 times the probability for 2 is 12 over 36, so 12 over 36 plus 3 times 6 over 36 plus 4 times 6 over 36, then finally plus 6 times 6 over 36. And let's punch this into the calculator. This is going to be, that's 1 times 6 over 36 plus 2 times 12 over 36 plus 3 times 6 over 36 plus 4 times 6 over 36 plus 6 times 6 over 36. And this gives us that our expectation is 3, and that is our final answer. Number 3. In Molimba, the heights in centimeters of adult males are normally distributed with mean 176 centimeters and standard deviation 4.8 centimeters. Part A. Find the probability that a randomly chosen adult male in Molimba has height greater than 170 centimeters. So we've got the heights of the adult males from Molimba being normally distributed with mean 176 and standard deviation 4.8. So variance is 4.8 squared. And we want to find the probability that an adult male, so probability that M is greater than 170. Okay, so we're going to standardize. That's 170 minus 176. And this is over our standard deviation 4.8. So the probability that Z is greater than, let's punch that into the calculator. This is 170 minus 176 over 4.8, and this gives us negative 1.25. We can rewrite this as the probability that Z is less than 1.25. So this becomes phi of 1.25. And if we read off the value of phi of 1.25 from our normal distribution tables, we get 0.894 correct to 3 significant figures, and that's our final answer. 60% of adult males in Molimba have height between 170 centimeters and K centimeters, where K is greater than 170. part B, find the value of k, giving your answer correct to 1 decimal. So we have been told that the probability that males in Molimba have a height between 170 and k is equal to 0.6. Okay, so let's standardize. That's going to be the probability of 170 minus our mean. Our mean is 176. All right, 176 over our standard deviation. What is our standard deviation? Is 4.8. And this is less than m, which is less than k minus our mean. So 176 over our standard deviation 4.8. And this is equal to, that's 0.6. So this is the probability that, let's simplify that. That's 170 minus, oh, we did simplify that. We get negative 1.25. So negative 1.25 is less than m, and this is less than, I'm just going to represent this as Z1, right? So that this is more readable. This is equal to 0.6. Like, because we have standardized, we should have this as Z, not as N. So looking at a diagram or drawing our bell curve, we are looking at something like this. We've got 0 here, and then we've got negative 1.25. So negative 1.25 would be somewhere here, negative 1.25. And then the area in between negative 1.25 and Z1 has to be 60%. So this means that our Z1 is going to be somewhere here, Z1, such that this area here is equal to 0.6. So if we want to find Z1, we just need to know what the area to the left of Z1 is. So essentially, we need to know what the area. We already know that from Z1 to negative 1.25, it's 0.6. What about this distance that is less than negative 1.25? If we can find that, then that will give us enough information to find Z1. So essentially what we want is phi of negative 1.25. This is essentially 1 minus phi of 1.25. 1.25. Phi of 1.25 we evaluated in the earlier question. It's 1 minus 0.8944 if we're going to be exact. So that's 1 minus 0.8944. That gives us 0.1056. So it means this area here is 0.1056. So the total area to the left of Z1 is going to be 0. Let me write it in blue. It's going to be 0.1056 plus 0.6. And that's 0.1056 plus 0.6. That gives us 0.7056. So to get Z1, we can say that this is arc phi of this whole area to the left of Z1. So let's find the Z value that corresponds to this area using our normal distribution tables. And that's going to be 0.541. All right. Now I want you to remember that Z1 was simply just a placeholder for K minus 176 over 48. So in other words, what we're saying is that Z1 is equal to K minus 176 over 4.8. Okay. So this means that 0.541 is equal to K minus 176 over 4.8. So multiply both sides by 4.8. So that's 0.541 times 4.8. This gives us 2.5968 is equal to K minus 176. So K is equal to 2.5968 plus 176. So therefore K must be equal to, that's 2.5968 plus 176. And this is 178.5 0.6 if we're giving it to one decimal place. Do they specify? Yes, they want one decimal place. So 178.6 is our final answer. Number 4. On a certain day, the heights of 150 sunflower plants grown by children at a local school are measured correct to the nearest centimeter. These heights are summarized in the following table. Alright, and then part A, they want us to draw a cumulative frequency graph to illustrate the data. So to be able to draw a cumulative frequency graph, you need two things. And the two things that you need are the upper bounds of your classes as well as the cumulative frequency for each class. Okay. But before we even get there, you will notice that we've got a serious problem here. We've got gaps between our classes. We do not want this gap. This gap from 29 to 30, this gap from 39 to 40. So we have to close those gaps. And the way we're going to close those gaps is simply add 0.5 to your upper bounds, and then subtract 0.5 to your lower bounds. Okay, so the idea is to just get your bounds to meet in the middle. All right, so our new table, after we have closed these gaps, this is centimeters, and then we're gonna have frequency on the bottom. Our new table should look like we're going to have subtract 0.5 from 10, that's 9.5, and then add 0.5 to 19, so 19.5. So our new lower bound here is 19.5 as well, and it's going up to 29.5. And we're going to do this for all of our classes. So this is going to be 29.5 all the way up to 39.5. All right. So this next class starts from 39.5 and it's going up to 44.5, and the next class starts at 44.5, and it's going all the way up to 44.5 up to 49.5. I think we've got another class that's going from 49.5 to 54.5, 49.5 to 54.5, and we've got another class as well. Okay, that's going from 54.5 to, that's going to be 59.5, and this is the final class. So we've closed our gaps now. That was the first problem. Okay. And the next thing that I want to address is, and the next thing that we would want to address is, instead of frequency, what we actually want is the cumulative frequency. Okay. So we want cumulative frequency. And so for each class, what cumulative frequency is, it's the frequencies of all the previous classes plus the frequency of the present class. So for the first class, its cumulative frequency is just going to be its own frequency. So it's just going to be 10. And then the cumulative frequency of the second class is the frequency of the first class plus its own frequency. So it's 10 plus 18, which is 28. And then for the third class is the frequencies of the previous two classes plus its own. So it's going to be 28 plus 32, which is, my math is very poor, that's 60. And then for the next class, that's the 40 to 44 one, it's going to be 42 plus 60, so 102. And then the next class, this class 45 to 49, 28 plus 102, so that's 130. And then for the next class after that, we add 14, so it's 144. And then for the last class, it should be 150 because we are looking at 150 sunflowers. Right. So we've got our cumulative frequency now. But we said what we are interested in are our upper bounds. So I'm just going to get rid of our lower bounds. So we can say that this is h is less than or equal to 19.5. And then this is h is less than or equal to 29.5. This is h is less than or equal to 39.5. This is h is less than or equal to 44.5. This is h is less than or equal to 49.5. And this is h is less than or equal to 54.5. And finally, this is h is less than or equal to 59.5. And I should probably highlight that this is h in centimeters. H in centimeters. Okay. And so now that we've got upper bounds against the cumulative frequency, we can now plot our cumulative frequency graph. All right, so we need to figure out what our scales are. On the y-axis, we're going to have our cumulative frequency. And then on the x, we're going to have our heights. And these are in centimeters. Okay. So for the cumulative frequency, let's count how many boxes we have. So we're starting here. That's going to be 0. We've got 1, 2, 3, and 4, 5, 6, 7, 8. Okay. We've got a total of 150 sunflowers. What is 150 divided by 8? That gives us 75 over 4. But we could do 160 by 8 so that we move in 20s, right? Yes, we can move in 20s. So this would be 0, 20, 40, 60, and this is 80, 100, 120, and we've got 140, 160. Okay, and we need a scale for the x-axis as well. So it's going to start at 0. Let's count how many boxes do we have. We've got 1, 2, 3, 4, 5, 6. What do our heights go up to? Our heights are going all the way up to 59.5. So we can move in tens. Okay, and just say 10, 20, 30, 40, 50, 60. Okay. And now we can go ahead and plot our points. I'm just going to reduce the thickness here. Okay. So the first point that you always plot is the point 0, 0. And then going to our table, we want 19.5, a height of 19.5 for the cumulative frequency of 10. So 19.5. Okay, 19.5 is going to be somewhere here, cumulative frequency of 10. So we're looking at this point right there. Let's go on to the next point. That's a height of 29.5, cumulative frequency 28. Okay. So 29.5 is somewhere here, cumulative frequency. Here we're moving by 2 units, so 22, 24, 26, 28. So that's going to be right here. Let's go on to the next point. So that is a height of 39.5, cumulative frequency 60. So 39.5, 60. All right, 39.5 is going to be somewhere here and 60 right there. And then we want 44.5, 102. Okay. So 44.5 is going to be just before this line. And we want 102. 102. 102 would be here. And then what's the next point? Got 49.5, 130. Okay. So 49.5 is going to be somewhere here, and we want 130. So right there. And the last point is going to be at, that's 59.5, 150. Okay. So 59, 150, where's 150? So 150 will be somewhere here, and 59.5 is going to be right there. And now we can just zoom out. Okay. And our job here is to join our points and form an S-shaped curve. Okay. So it's going to look something like this. Going through all of these points. Like that. This is going to be our cumulative frequency curve. And then part B says use your graph to estimate the 30th percentile of the heights of the sunflower plant. So 30th percentile, that's just 30% of our 150 sunflowers, because we've got a total of 150. So what is 30% of 150? 30 over 100 multiplied by 150. Let's punch that into the calculator. This is 30 over 100 by 150. That gives us 45. So we can draw construction lines at a cumulative frequency of 45, and we want to find the corresponding height. Okay, so where is 45 going to be? This is 42, 44. So 45 would be somewhere here in the middle right here. Okay. And of course, make sure you're using a ruler to draw these construction lines, but they should be there. They definitely should be there, because you get marks for showing your construction lines. Okay. And this is going bang in the middle, yeah. So this is 31, 32, 33, 34, 35. I'm getting 35 and a half. So I'll just give it exactly as it is, 35 and a half according to my diagram. Give your answers according to your diagram. So 30th percentile is 35.5 centimeters. Part C says calculate estimates for the mean and standard deviation of the heights of the 150 sunflower plant. Okay, so to be able to calculate our mean and standard deviation, we need the midpoints of each class as well as their corresponding frequencies. So we need a table of midpoints against the frequencies. Okay, so frequencies I believe we already have from the table at the very top. So our frequencies are 10, 18, 32. I'm just going to copy them down. We've got 10, 18, 32, and we've got 42, 28, 14, 6. 42, 28, 14, 6. Okay. And now we need to find the midpoint of each class. So you're just adding your lower bound to your upper bound and then dividing by 2 to get the midpoint. So for the first class, our midpoint is 10 plus 19 over 2, which is 14.5. So 14.5. And then for the second class, our midpoint is going to be 20 plus 29 over 2, which is 24.5. 24.5. For the third class, it's 30 plus 39 over 2, which is 34.5. 34.5. Okay. Then the next class is going to be 40 plus 44 over 2, which is 42. 42. And then for the next class, it's going to be 45 plus 49 over 2, which is 47. 47. And then for the next one after that, 50 to 54, the midpoint is going to be 50 plus 54 over 2, that's just 52. And then for the last class, that's going from 55 to 59, so our midpoint is 57. Once you've got your midpoints and your frequencies, you can now find your mean. To find our mean, x bar, we use the formula the summation of xf over the summation of f, where x are your midpoints and f is your frequency. So let's start by finding the summation of xf. Alright, so that's going to be the summation of xf is equal to, so 14.5 times 10 plus 24.5 times 18 plus 34.5 times 32 plus 42 times 42 plus 47 times 28 plus 52 times 14 plus 57 times 6. And so the summation of xf is equal to, that's 14.5 times 10 plus 24.5 times 18 plus 34.5 times 32 plus 42 times 42 plus 47 times 28 plus 52 times 14 plus 57 times 6. This gives us 5,840. So our mean is going to be that 5,840 over our summation of f. We've got a total of 150 sunflowers. So x bar is equal to 5,840 divided by 150. That gives us 584 over 15, which is approximately 38.9. Okay. But we also need to find our standard deviation. So to get our standard deviation, sigma is going to be the square root of the summation of x squared f over the summation of f minus our mean x bar squared. All right. So we need to find our summation of x squared f. So the summation of x squared f is essentially this long expression, except now you're going to go ahead and square all your x values. I'm just going to rewrite it here. This is x squared f. It's going to be 14.5 squared times 10 plus 24.5 squared times 18 plus 34.5 squared times 32 plus 42 squared times 42 plus 47 squared times 28 plus 52 squared times 14 plus 57 squared times 6. So that's the summation of x squared f. Let's punch this into the calculator. That is 14.5 squared multiplied by 10 plus 24.5 squared multiplied by 18 plus 34.5 squared multiplied by 32 plus 42 squared multiplied by 42 plus 47 squared multiplied by 28 plus 52 squared multiplied by 14 plus that's 57 squared multiplied by 6, and this gives us 244,285. So substituting into a formula for standard deviation, we get that sigma is equal to the square root of the summation of x squared f, which is 244,285, over our total frequency. We're dealing with 150 sunflowers minus our mean. I'm going to use this value, 584 over 15 squared. The sigma is equal to, that is the square root of 244,285 over 150 minus, that's 584 over 15 squared, and this gives us 10.6. So this here is our standard deviation, and our mean is right here. Number 5. A factory produces chocolates. 30% of the chocolates are wrapped in gold foil, 25% are wrapped in red foil, and the remainder are unwrapped. Indigo chooses 8 chocolates at random from the production line. Part A. Find the probability that she obtains no more than 2 chocolates that are wrapped in red foil. Alright, so we can consider this a binomial distribution. So we can say let R be the random variable, number of chocolates wrapped in red foil that indigo picks, that indigo chooses, that indigo selects. So R follows a binomial distribution. She selects 8 chocolates, and her probability of picking one wrapped in red foil is 25%, so 0.25. And we want the probability that no more than, so less than or equal to 2. Okay, so this means we're looking at 0, 1, and 2. So let's evaluate those probabilities. That's going to be 8 choose 2 times 0.25 to the 2 times 0.75 to the power, that's 6, plus 8 choose 1 times 0.25 times 0.75 to the 7 plus 0.75 to the 8. Okay, so the probability that R is less than or equal to 2 is equal to, this is 8 choose 2 multiplied by 0.25 to the power 2 multiplied by 0.75 to the power 6 plus 8 choose 1 multiplied by 0.25 multiplied by 0.75 to the 7 plus 0.75 to the 8. And this gives us 0.679. And that is our final answer. Jake chooses chocolates one at a time at random from the production line. Part B. Find the probability that the first time he obtains a chocolate that is wrapped in red foil is before the 7th choice. So we are looking for a first success. So this means this is going to be a geometric distribution that we're dealing with. So we can say let J be the random variable, number of chocolates Jake selects or Jake chooses until he finds a chocolate wrapped in red foil, in red foil. Okay, so J follows a geometric distribution, like we said, and the probability of getting a chocolate wrapped in red foil is 25% or 0.25. And we're saying find the probability that his first success is before the seventh choice, so less than 7. We can rewrite this because this is a discrete distribution. We can rewrite this as less than or equal to 6. And this allows us to use the idea that the probability that x is less than or equal to r is equal to 1 minus q to the r, where q is equal to 1 minus p. So in this case, in our case, q would be 1 minus 0.25, and that's 0.75. So we can say that the probability that j is less than or equal to 6 is equal to, that's 1 minus our q, which is 0.75, to the r. Our r is 6. So the probability that j is less than or equal to 6 is equal to, this is 1 minus 0.75 to the power 6. So this gives us 0.822, and that's our final answer. Kiefer chooses chocolate one at a time at random from the production line. Part C, find the probability that the second chocolate chosen is the first one wrapped in gold foil, given that the fifth chocolate chosen is the first unwrapped chocolate. Okay, there's a lot that's going on here. So the keyword is given. This tells us that this is conditional probability. And so let's define, I'll write the formula for conditional probabilities. The probability of B given A is equal to the probability of the intersection of A and B divided by the probability of A. So A is our given event, which is fifth chocolate chosen is first unwrapped chocolate. So fifth chocolate chosen, chocolate is first unwrapped, is first unwrapped. And then B would be the other event. Find the probability that second chocolate chosen is first one wrapped in gold foil, is first one wrapped in gold foil, wrapped in gold foil. Okay. And then the intersection of A and B would be fifth chocolate chosen. Fifth chocolate is first unwrapped, and second chocolate is first wrapped in gold foil. Wrapped in gold foil. This is a lot to write. Gold foil. Alright, so we need to find the probability of A and the probability of A intersection B. So let's start with the probability of A. Fifth chocolate is the first unwrapped. So we can define a distribution for A and say that A, because again we are looking for the first unwrapped chocolate, we're looking for a first success, this would be a geometric distribution. And we're saying probability of getting an unwrapped chocolate is what? It's the remainder. So it's 1 minus our 0.3 from here minus our 0.225. So what is that? 1 minus 0.3 minus 0.25, that gives us 0.45. Okay, so the probability of getting an unwrapped chocolate is 0.45. And here our interest is fifth chocolate is first unwrapped. So the probability that A is equal to 5. I probably shouldn't be using the letter A for the random variable, but oh well. So the probability that A is 5, that's going to be Q to the 4. So 1 minus 0.5 0.45 to the power of 4 multiplied by our first success, which is 0.45. This is the probability that A is 5 is equal to, let's punch this into the calculator, 1 minus 0.45 to the power of 4 multiplied by 0.45. This gives us 0.0411778125. Okay, I'm giving the exact value because I might want to use that for other things. Probably should not use A here because it's not going to make sense. I'll use U instead for unwrapped. U and then U. Okay. And so I guess I didn't mention this, but what we've just found, probability of the event A happening is equal to the probability that U is equal to 5. So the probability of A is equal to 0.0411778. Let's evaluate the probability of A intersection B. So we want the second chocolate to be the first wrapped gold. So I'm just going to say first chocolate, second chocolate, third chocolate, fourth chocolate, fifth chocolate. So the fifth chocolate is the first unwrapped. So I'm going to put a U there. And the second chocolate is the first gold. So let's put a G there. And so it means our only option is to have red first. Because if we put a U here, then it means this is no longer the first unwrapped. And if we put a G here, this is no longer the first gold. So in the first pick, we can only pick a red chocolate. And then in the third pick, this can be R or G. Okay. And then here it can be R or G as well. For the same reason, we can't pick a U in any of these two slots because this then won't be the first unwrapped chocolate. All right, so now let's evaluate the probabilities. So what's the probability of picking a red chocolate? Red chocolate is up at the top. Red chocolate is 25%, so 0.25. 0.25. And then gold is going to be 30%, so 0.3. Okay, so that's times 0.3 times, here we've got red or green, so we're going to add the two. Okay, so red is 0.25. Oh, this G is gold, not green. So that's 0.3 here. Multiplied by, again, we've got the same situation, 0.25 plus 0.3. And then finally, unwrapped. Unwrapped has a probability of 0.45. 0.45. Okay, so the probability of A intersection B is equal to, let's punch this into the calculator, that's 0.25 times 0.3 times 0.25 plus 0.3 times 0.25 plus 0.3 times 0.45, and this gives us 0.010209. Okay, so we can now find the probability of B given A. This is equal to the intersection 0.010209 divided by the probability of A, which is our 0.0411778. So 0.0411778. Okay, so let's punch that into the calculator. This is probability of B given A. That's 0.010209, and this is over 0.0411778, and this gives us 0.248, correct to three significant figures, and that's our final answer. Number 6, part A. Find the number of different arrangements of the 9 letters in the word happiness. So we've got 9 letters, so we do 9 factorial. Do we have any repetitions? Yes, we do. P appears twice, so over 2 factorial. S appears twice, So we've got another 2 factorial. Is there anything else repeating? I don't think so. So that's 9 factorial over 2 factorial times 2 factorial. And this gives us 90,720 different arrangements. Part B. Find the number of different arrangements of the 9 letters in the word happiness in which the first and last letters are not the same as each other. So we could think of this as just the total number of arrangements, right, which is what we got in part A, total number of arrangements minus the arrangements in which the first and last letters are the same. So first and last letters are the same, last letters are the same. Because if we remove the arrangements in which the first and last letters are the same, the only arrangements that remain will not have the first and last letters being the same. Okay, so the total number of different arrangements, that's part A, that's 90,720. Now we need to figure out first and last letters being the same. So we can either have P and P on either end, then there's 1, 2, 3, 4, 5, 6, 7 in the middle. So that can be H, A, and we've got I, N, E, S, S, or what we could have is S and S on either end, then 1, 2, 3, 4, 5, 6, 7. And then we've got that H, A, P, P, I, N, E. And so for this scenario here, we've fixed the P on either end, so we're not rearranging them. We're just rearranging the letters in the middle. So there's 7 of them, so 7 factorial. And the S's appear twice, so 2 factorial. And that's exactly the same thing happening here. We've fixed the S's on either end, so we are rearranging the 7 letters in the middle, and we've got the P's appearing twice, so we have to divide by 2 factorial. So I'm just going to multiply this by 2 because it's the same thing there. And so what we end up with is essentially just 7 factorial there. So 5,040. 5,040. And then we have to subtract this from 90,720 to get our final answer. 90,720 minus 5,040 gives us 85,680. These are the total arrangements in which the first and last letters are not the same as each other. Part C. Find the number of different arrangements of the 9 letters in the word happiness in which the 2 P's are together and there are exactly 2 letters between the 2 S's. Okay, so we're putting our P's together. Okay. And then we must have 2 letters between the S's. So 1, 2, 3, 4, 5, 6, 7, 8, 9 letters. All right. So that's going to be our H, our A, our I, N, E. All right. So for this scenario, for this first scenario, we want to prevent our P block to go in between the 2 S's. We'll do that calculation separately. So in fact, let me just put this scenario on the side where the P blocks are in between the S's. And then we've got our 5 remaining letters, 3, 4, 5. So that's going to be the H, the A, the I, the N, and the E. All right, so for this first scenario where we are saying that the P block cannot go in between the S's, we're going to say, firstly, we're rearranging 1, 2, 3, 4, 5 items, so 5 factorial. And then the S's, we can either have this S here or have it in this position or in that position or in that position. So we have to multiply by 4. And then the P block can either be at the beginning here, or it can come in this gap, that's 2, or it can come in this gap, that's 3, that's 4, that's 5. So it has 5 possible slots. Okay. And then coming to this second scenario here, we're saying that the P block is stuck in between the S. right? It's the only thing that can be there. So in fact, I should probably just block this as well. And so essentially we're rearranging 1, 2, 3, 4, 5, 6, because I want to fix the p block in between the two s's. So this becomes 6 factorial. And then we add the two scenarios together. So we've got, well, let me write it down here, 5 factorial times 4 times 5 plus 6 factorial. So 5 factorial times 4 times 5 plus 6 factorial. That gives us 3,120, and that's our final answer. The 9 letters in the word happiness are divided at random into a group of 5 and a group of 4. Part D. Find the probability that both P's are in one group and both S's are in the other group. So we could either have that 1, 2, 3, 4, 5 and 1, 2, 3, 4, and then 1, 2, 3, 4, 5 and 1, 2, 3, 4. So we could either have that both P's are in the group of 5 and then the S's would be in the group of 4, or the other way around, both S's are in the group of 5 and the P's are in the group of 4. So for this first scenario on top, we're choosing 2 P's from 2, so 2 choose 2, multiplied by, we've got 3 remaining slots here, 4. We don't want to pick the S's, so we're going to remove them from the selection pool. We've already selected our P's, and now we're removing the S's. Okay, so it means we've got 1, 2, 3, 4, 5 to pick from. So 5 that we want to fit into 3 slots. So 5 choose 3. Okay, and here what we want is we want to pick both S's into that group of 4. So that's going to be 2 choose 2 multiplied by, we've got 2 remaining slots for how many letters will remain. We've already picked 5 letters in this first group of 5, and we've picked the 2 S's. So it means only 2 letters will remain. So 2 choose 2 as well. So this whole row is essentially just 5 choose 3, because 2 choose 2 is 1. 5 choose 3, which is 10. And then the second scenario is essentially going to give us the same answer, because the problem is the same. We're going to say 2 choose 2 times 5 choose 3 again. And this is times 2 choose 2 times 2 choose 2. This is going to equal to 10. So that's going to be 20. Now, assuming there are no restrictions, how can we pick a group of 5 followed by a group of 4? So it's going to be 9 letters, choose 5, okay, followed by only 4 people will remain, only 4 letters will remain, so it's going to be 4 choose 4. All right, so what is our denominator going to be? It's 9 choose 5 times 4 choose 4, which is 1. So essentially this is 20 over 126, which is equal to 20 over 126 is 10 over 63. And this will be our final answer. All right, and that's the paper as well. So I hope you found this video useful, and if you did, please share it with other people who you think might benefit from this. And I wish you the very best in your exams. Make sure to like, subscribe, and comment down below if you want to get an A star. Bye bye. Good luck. All the best.